Good morning from Democritus. Welcome back. And I hope you are enjoying your school. Unfortunately, because of the lockdown, from tomorrow you'll probably be at home. Anyway, here we are. And today I'm going to speak to you about the three laws, Newton's laws of dynamics. You probably heard of them, or if you haven't heard of them, you probably do them at school sometime. The three laws of dynamics describe the important response of materials and bodies to forces. So how do forces affect the movement of bodies? The three laws, we're going to be mainly dealing with the third law of dynamics, which is the action-reaction, but let's remember the three laws. The first law is the law of inertia. Means that every body has mass, inertial mass, and the mass does not want to change a situation, does not want to move when it's not moving, or to change velocity when it's moving. So inertial mass, the higher the inertial mass, the more difficult it is to change the position of a body or the speed of a body. Just remember a huge man, how difficult it is to push him to change direction or change velocity. The second law is to do with acceleration. So acceleration means that in order to change the velocity, to give acceleration to a body, you have to exert a higher force, a larger force. You have to push much harder. So the larger, a car, you need to pull. In order to get a car moving, you need to really push hard. So if a car is motionless, you need to push harder in order to overcome its inertial mass, and then even harder to get it to accelerate. But today we're going to concentrate on the third law, which says that for every action, for every force, there's always going to be an equal and opposite force, a reaction. And that means that forces always appear in pairs. If I'm pushing against my one hand, the other hand has to push against the other. So those two now are a good pair. When I'm standing on the ground, the ground is exerting a force on me. There's always going to be a pair of forces. For example, if I'm weighing myself in the morning, there's a weighing scale, okay, and I'm standing on the scale. Oh, I've gained some weight, I must do something, or maybe calibrate the scale. Okay, so if I'm standing on the scale, so what I'm measuring is the reaction to my weight. And because the reaction is exactly equal, then I can trust, if I haven't done any mistake in calibration, that this is my real weight. And of course, in everyday life, we see this all the time. We're walking along, without reaction, it will be very difficult to walk. There's elasticity in the shoes, of course, elasticity in the ground, but of course, even a ball, dropping a ball and playing with a ball, illustrates and demonstrates exactly the action and reaction. There it is. So whenever I'm pushing down, there's a force on the ground exerts a force back, and of course, there's elasticity of the ball as well. So all these things are pairs of forces. Now, in science, we actually use and exploit this, and one of the ways of exploiting is to measure the strength of materials. So here we have a large machine. This large machine is able to measure strength. It actually compresses, it stretches, it does all sorts of things with materials. And here I'm going to set it up to measure the strength of this piece of wood. This over here, this what we call cross piece, comes down at a certain speed and compresses that wood, and we measure the reaction of this force, the reaction of the force from between this side and that side through the electronics, and the reaction comes onto because of electronics, we send it to the computer, and the computer gives a graph and everything, so we can measure reaction, we can measure. Another time we'll do a full experiment and I'll explain to you in terms. Now, action and reaction, the pairs of forces, are, as I said, everywhere. A car driving, and most importantly, a rocket. Now, a rocket in space. A lot of people ask me, how on earth is it possible for a rocket to fly in space? Well, it's very easy. A rocket spews out material from below, from the conical nozzle. So when it spews out material at high energy and high mass, that material goes one way. So because of the forces that are exerted, the rocket has to go the other way. And that's a very nice example, an excellent example of the third law of Newton. And of course, the next week or this week sometime or next week is the Chinese New Year. And what better way to illustrate the rocket the rocket which was actually invented. A rocket with fuel was invented by the Chinese. The ancient Greeks knew about the rockets because they played around with rockets with steam. And today we're going to demonstrate action-reaction with rockets, but in a different way. So let's go and play with rockets. Okay, what have we got here? We have 4 lovely rockets. They look like bottles of Sprite or whatever it is, but they will be our rockets. So what we have in here, we have water. So I've actually half filled the rockets with water. And you can see over here is water, and the rest is gas. Now the water will be coming out of a hole here. I've got a hole in each of these cups. So the water will be actually our propulsion. So the water will be coming out at high force and gives us that propulsion, will give us the rocket, the force. But how do we exert the force? The way we do it, we play with liquid nitrogen. Now liquid nitrogen, let me move this chair out of the way. Liquid nitrogen is a lovely stuff. It's the air we breathe. Most of the air we breathe is of course nitrogen, and some oxygen as well, of course. But liquid nitrogen is a lovely stuff, and you can see it's actually liquefied air. When we cool down air, then even on the table, it's liquid. And this liquefied air is at minus 196 degrees. When we cool down air to minus 196, it becomes liquid like that. So, and because it's warm in the room, the liquid air, the liquid nitrogen evaporates very quickly. So it actually creates a gas, a high pressure gas inside the bottle. So I'm filling in the bottle, quickly closing it, and you can see it's evaporating. And I'm going to go outside. Wow, that was a good one. All right, I don't know if you saw it, but the compressed air inside the compressed gas, because of the evaporation, is giving a big force onto the water. The water is coming out of the little hole, so it makes it like a real rocket. Now let's do it again, but this time we're going to put an astronaut. A little astronaut. It's a little Valentine's astronaut. Can you see? It says, "I love you." So we are sending the little astronaut over there. I love you. There you go into space. I hope he survives. So let's put the astronaut, and because the rocket goes upside down, so there you go. I'm going to put him hugging the rocket. There you go. Oh, I'm going to I must put him upside down because the rocket will go that way. That's a little astronaut. There you go. Now let's do it again, and I hope this poor astronaut will survive the trip. Liquid nitrogen, a little bit more. Quickly close it. And here we go. The little astronaut survived. Let me have a look. There you go. He's safe. He's safe. He's very good. He's good. He's good. He's safe. Let's do it one more time because up to now all the rockets are going like that. So let's try one more time to see if we can get the rocket to go straight. But you can see the reaction is so strong because the water is heavy compared to gas. And of course, because it's heavy, whoops. Whoa! The propulsion is so strong that it actually pushes the rocket, it pushes the bottle all over the place. Anyway, this is the third law of dynamics. We just said law of dynamics. And I'm a bit wet, so I think I'm going to call it a day. I hope you enjoyed it, and remember that action and reaction, actions and forces always occur in pairs. Until next time, goodbye from Diogenis.